Thank you. So, hello everybody, I'm Timo. I came all the way from Cologne, which is not that far, but yes, actually it's cold here. I thought we are in the south and it would be, you know, sunny and warm, but so yeah. We at Giant Swarm, we are building an infrastructure for microservices. This is kind of a funny story. We together as founders quit at the last company and decided to start something new. And so we were on a green field and had to look for ideas, what we can do, and we were exploring all kinds of like med tech and agriculture, like drones flying on fields and detecting with colors of the plants if there's some water needed or something like that, and fintech, and we were just exploring it, and I'm the tech guy, so I was just exploring what could be the next infrastructure to run that product on. And we did microservices and had the polyglot infrastructure at the last company, where we had like nearly all the NoSQL stores that are out there. So we automated that infrastructure and we put a lot of effort into it, but I wasn't happy with it. And so I was just exploring, and then, you know, containers came and I was just playing around, and everybody we showed that was either saying, okay, can I work in your company because it's really interesting and I want to do the same thing, or can I have that because I really need this? And at one point we suddenly figured out that we had this big Excel spreadsheets where we evaluated the ideas, and then we put the infrastructure in, and we suddenly found out this is the thing we want to do. We want to build a product for developers, and we want to have a tech company where we have a culture for developers, and we saw that need because we had that before. And we wanted to take away that pain from other companies so that they can focus on their products and don't have to waste time to automate the infrastructure. So we're building that infrastructure with microservices itself. So we're dog fooding here. We have, I think, around 110 repositories on GitHub right now. We're 16 people, and we really have small services, and so we're launching our own stuff on our infrastructure to build that infrastructure, which is kind of interesting. Yeah, so you all know about microservices. That's why I made this little story. To make it short, to just have a background, like an introduction to it. So there's every Pixar movie has an outline, which is once upon a time, every day, one day, because of that, until finally. When I picked that outline and made a story out of it for microservices. So once upon a time, there was a small web app. You know, there are two always, because you want to have like N+1 redundancy so you can sleep, right? So every day new features were added and the user loved it. One day it became very hard to maintain and to add new features and to scale it. Because of that, popular features were put into separate services with their own databases. Because of that, server and deployment was automated. Until finally, more popular features could be added easily. Yeah, and this leads to, you know, all that, 2 pizza teams, you can have feature teams, you can have like organizational benefits from it. we had this in the last company, and I think it was a huge benefit. Everybody learned from each other. We had like those T-shaped people in the teams that are very good in general and have a lot of knowledge, but have certain deep knowledge at some points, and they could work together with other people and transfer that knowledge and so on. So I really like to have these small teams that are independent from each other, so they can deploy independently and they can be autonomous. And yeah, one thing is throwaway services. I don't think that we're writing services to throw them away, but it's if you're in unknown territory and you have to explore a little bit, then it sometimes really helps by just writing a service, measuring it, like the typical lean build, measure, learn. You write something, you figure out it's not the right thing, it doesn't work, it doesn't help us, so we can just throw it away because it was just maybe a couple of days of work. Thank you. Yeah, these are the benefits of microservices, but I'm not here to talk about the microservices itself. I'm talking about it's not free lunch, and why it is hard to actually have a microservice infrastructure. So in theory, the ops guys, I would tell, this is how developers look at microservices. So it would be some resilient structure that is like becoming kind of like elastic or concrete, and it helps you to build an architecture that doesn't fall over that easy, because you have circuit breakers and you have small tools, and if one doesn't work, it doesn't matter, your app is just running and cope with their failures. So, but in reality we have these Death Stars, and this is how it actually looks. If you look at the, if you've seen a talk from Adrian Cockcroft, these are his examples from, I think that's Netflix, Guild, and Twitter. Yes. So the complexity is not gone. It's just that the complexity is moving to the infrastructure. And if you take yes, so in thermophysics, if something is unordered, there's a term for it. It's entropy, and it falls under the law of like energy. Energy is not lost. So if you remove entropy here, it's moving over there, and it's kind of that. So you're not losing the complexity of a distributed environment. It's more that you're moving it. And with what I want to show you with the containers, we have a clear modularization of apps and infrastructure, and a lot of that complexity that was former maybe within the apps itself is now moving to the infrastructure. So yeah, let's create immutable artifacts. I mean, this is what we have done at the last company already when we created AMIs on Amazon that our apps inside, so we could use the autoscaler to spin up new machines. But we also had autoscalers that actually spawned new machines, and then there was a chef client installed and fetching the chef recipes to install the software on it. So we did both. We had some systems building those AMI images, and we had other systems that were actually installing at runtime. And provisioning at runtime hurts a lot because it takes a lot of time. So if the server spins up and the chef client is installed and then the recipes are run, you end up by having autoscaling that takes 20 minutes to add a new server. And if you're under load and you want to have new capacity, it's really bad to wait 20 minutes. And it could even happen that, you know, I don't know, GitHub is not available and the server falls over because it couldn't fetch the packages. Or you didn't pin down every single version of a package and something has changed, maybe just a minor or a patch version, and things behave differently than you have tested before. So installing at runtime was something that was really bad. So creating that immutable artifacts beforehand is really important. And creating smaller immutable artifacts really helps. Because with that AMI, there was always, either we decided to put like software together inside that image, or we decided to run one single service on a server. But then if you take really small Amazon instances, for instance, you have bad network and you have to cope with other problems. And you cannot, it's not easy to decide which software should be run together on a server and to cut that right. So with smaller artifacts, containers, all things will be good. So I'm telling you a little bit about what we've come up with to make that easier to start containers in an infrastructure where you have zero configuration and have a runtime environment that your images do not have to be aware about the runtime environment. You can run them on your laptop and you can run them within our infrastructure, but you don't have to configure things within that images to run in production. So let's take a simple three-tier application, and this image is actually from the CoreOS website. So you have empty batteries? No, it was off. So you have a load balancer, an app container, and a database. You probably want to start the database first. So the database is scheduled here. You start the app container. It's trying. It doesn't know where the database is. So the database has to communicate to some central storage. etcd is a key value store that is optimized for consistent and network partition tolerance. So it's available but not highly available. So if the majority of the cluster is down, it won't be accessible. But it contains consistent information. So it's, if you're maybe familiar with Zookeeper, it's kind of similar to it. So the database would talk to etcd in that case, and the app container can talk to etcd and find out where the database is, and the same thing for the load balancer. But you could also do something like this. You can add another container that lives right beside your database. It's co-scheduled to the same host, and it actually watches the database coming up and then writing that information to etcd. So your database image doesn't have to know if you use console, etcd, Zookeeper, or whatever to store that information. This little sidekick container knows how to do this. So you can run any kind of database that is in a Docker hub, and it will be announced by your other container. And on the other side, you can add an ambassador, and in the container world, it's called the ambassador pattern. So the ambassador is co-scheduled to the app. So it lives right next to the app. And with Docker, you can link containers. So the ambassador would actually be linked to the app, telling the app, I am the database, but in fact being a TCP reverse proxy that talks to the real database over here and reading that information from etcd. So the app also doesn't have to know how to do service discovery in that infrastructure, because you can take a normal image, a Docker image, that you can run and link to, on your notebook, and run it in that infrastructure, and it works. Because with Docker links, you have either the link container in etc host as a host name you can access, or you have environment variables that you can access, similar to what you have on Heroku, for instance. If you have an add-on on Heroku, you will get the credentials to access that container in the environment of your process. So you can run this setup on your local machine, but you can also run it on an infrastructure where it doesn't run on a single host, because Docker links just work on a single host and not across hosts. So let's do some demo. I have to switch here. Can everybody read this? Yes? Fine. So the first thing I do is I'm creating that chorus cluster I showed you. If I can type my password. I do this a little bit different. You can do this in Vagrant instances. I do this in containers. So I start containers in containers. So actually I have now three containers running that run by systemd and spawn. So there are all the necessary tools from CoreOS running inside containers. It's way faster than starting virtual machines. Actually, so I just recreated it. So it's really fast. I think having containers on your local development environment is really fun, because you can do this kind of things. I always said if you have a full-blown IDE, you tend to produce bloaty software. So if you're using VI, then you're most likely to tend to actually create microservices, because you don't have all their tools that help you, and you won't produce that bloaty software. So I think the same thing goes for the infrastructure. I have a shitty network internet connection at home. I live on the countryside near the Dutch border, so it's really bad. Up until 2 weeks ago, I had a really old Lenovo. Actually, I had to do this in containers because running this in virtual machines and creating virtual machines and transferring them over the internet would be a pain in the ass for me. So now I have this 3 containers, and this is, anybody familiar with CoreOS already? Nobody. So I don't have to explain what I'm doing here. No, it's a tool coming from CoreOS called Fleet to actually launch things on that cluster. And I have an alias called Flocken Commando that talks to my containers, but it doesn't matter. So what you can do is you can list the machines and check if actually the cluster, it takes too long. Those cluster nodes found each other. The demo goes, oh, there it is. Okay, those nodes found each other. So this is done by etcd. So there's a discovery. Those nodes know each other, and now you can schedule things on top of it. And I'm starting. No, actually, I want to show you what I'm doing. So I'm starting part of our stack on that 3 machines now. So we need some utils, some scripts. These are the utils. It's like the start pre you see here is patching the container, and it's already installed and running. There are a couple of more services. So we have our own services discovery here, a service proxy. We have a gateway to the internet. Actually, there's also Weave in it, which is an overlay network, so that each container has an IP address and can talk to another container by accessing it directly. Normally, with Docker, you have a nutted network, so you have the IP address of the host, and then you have local IP addresses for that containers. So most of the time you use port mapping, map a port from the container to a port on the host, and then talking from another host to that mapped port, which is then redirected to the container. But in some situations you want to have direct access to the containers, especially if you want to run database clusters on it. With Weave you have a full layer 2 network, which means, and this was a requirement for a customer, that you can do multicast on that network between the containers. So you can actually use the multicast of Elasticsearch, for instance, to discover the Elasticsearch nodes. Or you can use something like Vertex, which also has a multicast discovery. So you also have a transparent service discovery there. You don't need to configure something. Yeah, and the routing layer is basically a proxy that accepts incoming HTTP traffic and sends it to the right containers. So. But to show you some, no, it's this one, right? To show you some of the things we have implemented right now. We came up with this JSON format to define a microservice or multiple microservices. So the idea was, how can we map the architectural thoughts around software on infrastructure? And I thought, okay, you definitely have an app, and this app will have multiple services, and those services will have multiple components. And what I don't want is that I have service A and service B, and they communicate through through a database. So I want to have like something where you define which is the endpoint of this service, and the other service can only talk to that service through that endpoint, but not being able to talk to a component within the service. That was mostly the idea behind this hierarchical structure. We now figured out that was not a really good idea, because there are a lot of people that have software that runs already and does communicate through databases, and actually we don't want to enforce that on our users. They might even have valid reasons why they do this, and so we want to help them, and if they have something that is not in an architectural way clean, it's totally fine to run this, and we don't want to be in their way. So we're currently working on a much leaner and flattened structure. We use label, similar to what Kubernetes does, but we also still support that hierarchy, because we figured out that some people really like to see that hierarchy, and labels can become a mess. If you look at the Death Star, then you really don't know which label is talking to which other label, and it's like kind of confusing. So if you like and you don't have that huge infrastructure or architecture, then you probably like to still have that hierarchical way to define things, where you can say, okay, this is service A, and to this service belongs component A, B, C, or you even have like a deeper level, and you can actually define some of the configuration to that subtrees, which makes it easy, instead of applying all those configuration options to labels. That might be confusing. So this ping is a small Go app that just replies with an hello, and I launched this on our server, on our warm up. There will be some units appearing here when it says that it creates something, but it doesn't. Let's do a swarm ping. Okay. Yeah, I don't know. So it starts the ping application, and somehow we don't see anything. There they are. So it starts a couple of containers, and this is what I said with the sidekicks. So it starts some of our sidekicks, and then in the middle here is the actual ping container that comes from the user. So we're configuring some parts of the infrastructure to actually run that container, and now we can actually look at the status, and we will see, yeah, there's a ping service from that Docker image, and it has this instance ID, and we can even do a swarm exec to actually enter that container. So now I'm within the infrastructure inside of the container. If I want to debug things, so I can see the network configuration, for instance, or I can look at the processes running. This is the ping service that was initially started, but and this is the shell I just opened, and I can just go out of the container again and ping the transform IO, and it says hello. So this was done by the domain configuration right here, which is also kind of confusing because it doesn't say it's ping localhost 80. It actually says, okay, use port 80 of this service. We definitely have to optimize that because a lot of people stumble upon that, but yeah, you can define a domain for each service, and this will actually register that domain within the routing layer, and the traffic will be redirected to that container. And so if I go back to my slides, I like to compare this with dependency injection, because you have containers that contain things that have a single responsibility, and for us that makes it really easy for us to actually change things within our orchestration. So if we want to implement a new storage, or if we want to implement a new network, then we just have to change that small component, because we can inject things with that sidekicks around the containers. So this is a container chain, how it could look like. You have a container that actually fetches the container of the user. You have a container that configures storage. On Amazon, for instance, this creates an EBS volume, attaches that to the host, mounts it, maybe formats it, and then later it's bind mounted into the container. And if that container is shut down and moved to another host, we will move that EBS volume over to the other host. And the same thing for network configuration. We can do, we can decide which IP address, which subnet this container will belong to. And we configure that beforehand. So we open up a network namespace within Linux, and the other container will later on join that network namespace. And that's the container. And at the end we do a service registration, where we announce that this container is actually run. And this container is, in this chain, is a single deployable unit. Those belong together on one host. And the funny thing with something like etcd is, you can even do that in a distributed way. You can create those chains across hosts. So we have the ambassador here, and within systemd you have functionality that lets you announce if a service is ready. So this is waiting here. The process already started, but the process didn't communicate to systemd that it's ready. So it's just sitting here and waiting. While here we start the storage config, the network config, the database, the service registration, and then the service registration will tell our service discovery, hey, there's the database. And this ambassador was still waiting, oh, there's the database. Okay, I can start the rest of the chain. And this is really nice because you can gracefully start an application and shut it down. It's not you just throwing all the containers on your infrastructure and you have the app failing, reconnecting, errors in your logs that it cannot communicate to the database. Because when we start the service, we actually know that the database has to start first and then the actual container. Of course, your container should reconnect if the database is not available, but in a testing environment maybe, where you start and stop applications and want to test things, it's really nice to have no errors. Yeah, and for fun, by the way, the whole setup works without internet, so I did this in a plane. And I thought, yeah, to show you how complicated distributed software is, I created the distributed hello world. So actually I have a component producing EL, LO, and H, and the same for world, and then have the API, which actually talks to service A, the service, hello service, and to the world service, and fetches the output and gives the output to the user. And I'm gonna run this. No, I can show you what I've used for it. So I created a small Go binary that I called concurl because it concats output by calling an URL. So this is actually done with the linking. So hello is the host name of the hello service. So within that container, in etc hosts, there is an entry hello with an IP address I can talk to actually fetch the data from that hello service. And I can do the same thing for world, and the same thing is here, and then all those services add a certain payload. And now, going back to my terminal. So this swarm JSON is a little bit more complicated because it's JSON, it's not very easy to read. You know, it's better than XML, but yeah, you have the service hello world, and here are the arguments for the concurl binary, and I tell that component that it has a dependency to hello hello and world world, and it has a domain hello world, and the hello service has 3 components, one component hello, one EL, one low, and so on. Like I showed you in the diagrams, it's much easier than reading the JSON. And I do a swarm up here. So you will see a lot of containers now. Yeah, actually it does something on the first one. So you can see that you see those things belong together because they have the same hash in the beginning, but those are scheduled to different hosts. You can see this one has 34, 13.2, 13.3. Some are together on some machines, and yeah, it's running. So you can do the swarm status. You see your services running, and fingers crossed you can curl hello.local.giant swarm IO. Hello. Yes, I gave domains to every service, so we can see the services itself, and then we can look at the output together. And the great thing about this is you can just easily, I can just squash the whole environment by just doing the rebuild of the cluster, and it's all gone again. It just takes me a couple of seconds to spin up that complicated infrastructure, that complicated services that can talk to each other in a couple of seconds. If you create this distributed software, to have this on your laptop, or this in a testing environment where you can actually easily spawn up those services and shut them down, it's really helpful if you can do this with such an ease, without configuration, and spin up your software. Yeah, that was the demo, and I'm at the end of my talk, but you can ask questions. You were really silent. I didn't expect that. So please ask me whatever you want to know. Nobody.
Maybe you're gonna help later.
A beer. Cheers. No questions?
Okay, I got one question with regards to etcd.
Yeah.
How do you, where's etcd living?
On each of the machines, the picture is confusing because it looks like it's separated. Usually it runs on each of the machines in CoreOS. So you're talking to localhost etcd, and you can get the information you want to have. In a production setup, it's different because it doesn't scale. It doesn't scale to more than 7 or 9 nodes, and you're probably better using 5 nodes. It's an important part, the critical part of that infrastructure, and you would probably put etcd on a couple of machines that you treat a little bit different from the other cattle. So a little bit more like pets, where you take care that those machines are not going down. Because if you have a 5-node etcd cluster and you're losing 2 nodes, you're fine. But if you lose the 3rd node, it's not accessible anymore. And especially on Amazon, if you have an autoscaler and an etcd, this is kind of bad. But they improved with the etcd 2 version. They improved that behavior because with the first version you could really host the whole database. So if the autoscaler terminated 3 machines and you're still left with just 2, you cannot join a new one, and those 2 are not accessible anymore, and you cannot remove those nodes. So you're actually screwed. You have to start a new cluster and copy over the data. But they optimized that. So in a test setup locally, if you use Vagrant, for instance, you will have etcd on the CoreOS machines itself. Kubernetes also uses etcd, and a couple of other projects. I think the new OpenShift from Red Hat. I think they're even using Kubernetes. So yeah, it's in a couple of stacks right now. It works with the Raft consensus algorithm, which is a little bit simpler than Paxos, which is kind of used in Zookeeper. Yeah, the reason is to have a key value store that is highly consistent and network partition tolerant. So if you have a split in those, better use uneven numbers and not equal numbers, because then if you have a network split and you have 2 machines here and 2 machines here, none of them would work. So if you have a network split with 5, you have either 2 here and 3 here. Only the 3 will work. They will elect a new leader, and they will keep on going, but the 2 will not be accessible. So nobody can write stuff to it that has later has to be resolved because different writes to the same keys.
I have 2 questions. Do you have any IoT use cases that you're working with currently? And the second question, do you have any use cases around SAP HANA, or say like with NoSQL and SQL?
So we don't have use cases with SAP software right now. We have a couple of customers that actually run dedicated environments because we have one infrastructure where we have a shared environment where we currently have alpha users that can play around and test and give us feedback. But we have a couple of reference customers where we work in dedicated environments. And yeah, those are running quite complex architectures. So for instance, Vertex microservices or something like Storm, where you have a distributed way to have real-time analytics. And yeah, so the use cases are at the moment mostly open source software plus applications coming from our customers. So it includes databases. So you can run Elasticsearch. We run Elasticsearch ourselves. We run InfluxDB. You can run Cassandra, Galera, things like that. Yeah.
Let's figure out I have 1 petabyte of text data, and I want to process the petabyte until tomorrow.
Yes.
How could you help me?
You could use whatever you use to do this and run this on our infrastructure. You just have to put your software into containers.
Could you give me, let's say, 10,000 machines or 10,000 CPU cores or whatever until tomorrow?
No. We can do this on Amazon. That wouldn't be a huge problem. But we're currently building our own infrastructure in Frankfurt with bare metal. So the containers will run on bare metal, and we wouldn't be able to provision machines like physically into the racks that fast. So yes, the stack runs on Amazon, and you could do this on Amazon, of course. But I'm not quite sure if everything within our stack right now would scale up until 10,000 machines. I would presume things will fall over. Yeah.
How are you provisioning your Core OS instances?
Provisioning is like you have an immutable image of Core OS, and you have a YAML configuration called cloud config, where you can actually define the first services that are started, some configuration parameters, how does the etcd nodes find each other, what do you do with networking, but there's no need for something like Puppet or Ansible, or so we don't need this. Yes?
Are you supporting port ranges? So can I map not only one port for the whole range?
You shouldn't map anything. We are not mapping anything in there. So within the shared environment right now, we don't have that interconnectivity between containers where you can talk to an IP address that is your container, and then you have the full port range. It's totally fine. We just support that in the dedicated environment right now, but we're currently working on integrating a networking solution into our orchestration that solves that for the for the shared environment as well.
So if I have a system that negotiates port
Yes.
ranges, like a cluster,
Yeah.
run
Or
this.
Erlang, this is a typical thing you have with Erlang, that you have like negotiation of which port the next connection will be on. Yeah, it's no problem.
Do you have an in-house solution with regards to collecting log files from the containers?
Yes, so we have an Elk stack where we collect all the information from the containers. And for the shared environment, we're currently working on a web UI where we where we provide that to the users. You can also do this with the command line interface, so you can actually query the Elasticsearch cluster about your containers with that swarm CLI I just showed you, and in the dedicated environment you can even have your own Elasticsearch, and we will just forward all the logs to your own Elasticsearch, so you can run your own Kibana and have more freedom to do whatever you like with your logs. Yeah?
I want to come back to your encapsulation you provide. So you have this service which encapsulates components. So you have one level of encapsulation. Can you do multiple levels of encapsulation?
That's what I said, that this really, so we try to have semantics in that JSON file, but it really didn't work out. Some have flat, and some have even deeper nesting. So yeah, the new format will be flexible and support more dimensions if you want to do that hierarchically, or if you want to do this with labels, you can do whatever. They're much more flexible with labels.
Do you support system D units if you don't want to make containers? Let's say if you're running like a Go application that's got 0 dependencies.
Not yet. We could do that on the dedicated environment where you're definitely the only one on that host. And but we're running everything in Go, and we're just building really small containers and running those. It gives you a benefit. You can do this with systemd, of course, but it's much more portable if you have that in a registry, for instance.
You got support for Rocket?
Sorry?
Rocket?
Yes. Docker gives us a lot of problems in production, and Rocket will help us a lot with that. And I think we will move over our own services to Rocket in maybe a matter of month now, because I think the features of Rocket are now at a point where I think we should move, and especially the systemd integration with Docker is actually non-existing, and running Rocket containers will really help a lot. The thing is, and the question for me still is, do I want to run user containers in a different container engine? Because I don't think that Docker will go away from the laptops of the developers. And I really like that. And it's really easy, and Rocket is not made for that. Rocket is made for production. If I see a problem with dev prod parity, that I have to, I don't know, replicate Docker bugs within Rocket to actually do the same thing that Docker container does on the laptop of the developer, I would rather run that container in a Docker container instead of Rocket. Yeah, but we will definitely move over our Go services to Rocket.
You've shown in your demo a swarm up and afterwards destroyed your swarm. How about a swarm upgrade, a new version?
Yeah, there's a swarm update where you can launch new versions. And we even do rolling updates with our own components right now. It's currently not exposed to the user. We are also working on how to deal with structural changes, because that's currently not implemented, and so there will be things
The structural
coming up.
Changes in the JSON file.
Yes, yeah, and I think you should help users doing this. I don't know if you looked at Terraform from HashiCorp, they do plans, and this is kind of nice to see actually what the infrastructure will do with that change you trying to do right now, and maybe to change that.
I would have a question. You're talking about Go services. Why especially Go? Is there any preference or?
We have mostly Python and Go, and in the last company, and a couple of developers were already with me in the last company. We only did Node, Clojure, and Ruby. So we're just trying out new things. No, actually, right now, none of the developers wants to go back and write any Node.js code anymore. Or, yeah. So we're quite happy with Go, and yeah, it's a lot of fun. Some more beer? Yes. Okay.